So here we're looking at this set again. This is the third video in a row we've started out with this set because it's a beautiful set. This set is what you call a basis for R2. And a basis for a vector space is a set that spans the vector space and is linearly independent. So a vector space does have lots of different bases. So this is a basis for R2 because it's linearly independent and it spans R2, so you can get any vector in R2 by taking a linear combination of these two guys. So the set 2, 3, and -1, 5 is also a basis for R2 because it's linearly independent, and which you can check, and it spans all of R2, which you can also check. So, and you'll notice that both of these sets that are bases for R2 have two elements in them. That is not an accident, because if you look at the set, say 1, 0, 0, 1, and when you put 2, 3 in there, I think that's what I did before. This is not a basis. Why? Because it's dependent. So it satisfies one condition. It definitely spans all of R2, but it is not independent. It is linearly dependent. So it's not a basis. And it has more than two vectors in it. And also if you take the set, say just containing 2, 2, I meant to write 2, 3, but 2, 2 is good enough. This is also not a basis. Because while it is independent, the only way to write the 0 vector as a linear combination of that one vector is to take 0 times it. So just the trivial way of writing the 0 vector. So it is dependent, but it does not span. So if you get too many vectors, you end up with a dependence. If you get too few vectors, you end up with something that doesn't span. So the number of vectors in a basis for a vector space is fixed, and that is called the dimension. So we're defining two things here. The basis and the dimension of a vector space is the number of elements in a basis. And like I say, that has to be fixed. So we have two different bases here, but they both have two elements. Now, this is a very nice one. This is called the standard. Because it's not just a basis, it's like the nicest basis for R2 because it's got these beautiful vectors. You want to write something as a linear combination of these two guys. You don't even have to think about it. If you want to write -5, 7 as a linear combination of these two guys, it's -5 times the first one plus 7 times the second one. Now this one you can write -5, 7 as a linear combination of these two guys, but it doesn't leap out at you what your coefficients would have to be in that linear combination. So that is basis and dimension. And standard basis. So here we have the standard basis for R3, and I think with the example of the standard basis for R2 and the standard basis for R3, you can generalize to the standard basis for Rn. And so this is a basis for R3. It's got 3 vectors, so R3 is dimension 3. R4 is dimension 4. R5 is dimension 5, and so on. Some other vector spaces we've looked at, and this set we've looked at. This is the standard basis for P2. This is the set of polynomials of degree 2 or less. So this is a basis, and not just a basis, but the standard basis. It's got 3 elements. So P2, sorry. Okay, let me scroll that out. P2 has dimension 3. So unfortunately, P sub 2 is a three-dimensional vector space. It'd be nice if all the numbers matched, but they don't. Last time we looked at set, I think we looked at this in the last video, 1 0 0 0 0 1 0 0 0 0 0 1, and what am I missing there? I went in the wrong order. It's alright, doesn't matter. So I got one wrong there. This is the standard basis. For M22, the set of matrices, the set of 2 by 2 matrices with real entries under the usual operations. And so this is a 4-dimensional vector space. Which should be fairly intuitive, because you have 4 positions you have to fill. Again, M22 is sort of equivalent to R4. And so these are the 3 types of vector spaces that we've looked at a lot and will continue to look at a lot in here. And so that is basis and dimension. And now you know what it means when we say that R2 is a 2-dimensional vector space and R3 is a 3-dimensional vector space, and so on. Okay, very good.